Hello, I'm Varsha Dani, and I'm going to talk today about energy-aware computation in radio networks, focusing mainly on some results that were presented at PODC 2020. This is joint work with Yi-Jun Chang, Tom Hayes, and Seth Pettie. So imagine a forest in which you have a number of fire detection sensors scattered all over the forest. And when there's a fire, the nearest sensor detects it and it wants to transmit the signal that there's a fire across this network of these sensors. And eventually, hopefully, the message has propagated through the entire network and reaches some sort of control station where they can act on the signal and do something to stop the fire. So the setting is that we have a lot of cheap devices, such as these sensors, and that they're arbitrarily scattered rather than being strategically positioned. And we have radio communication between the devices. And the most important point is that because they're little devices, they have a limited amount of power. So local computation is cheap, but communication is expensive. And previous energy models counted the number of transmissions. However, it's becoming increasingly clear that as devices get smaller and smaller, the cost of listening, the cost of just having your receiver on to hear a signal from a different device, also uses an amount of energy that's comparable to the cost of sending. So listening uses energy also. And so if you were able to adaptively power off the receiver, that could significantly prolong the battery life. So let's look at a toy example. Again, we have our sensors in the forest, but imagine that there are n sensors in a straight line. So when there's a fire, the first sensor detects it and it transmits, and the second one hears it and it transmits, and so on, and the signal travels down the line and hopefully gets to wherever something can be done. And how much does this cost? Well, it takes n time steps for the signal to go across the path of length n, and each node sends once, but the number of listens per node is order n, because even though the second node only has to listen for one time step, the last node has to listen for the whole time, and more than half the nodes have to listen for a linear amount of time. So, so this problem has 1 cent per node and order n listens per node. Now look at a different example. Suppose, again, the sensors are on the line, but they know exactly where they are. So now they can go to sleep, and node I is going to wake up at time I. So when the first node transmits, the second node is awake at just the right time to hear it, and then when the second node transmits, the third one's awake just at the right time to hear it, and the fourth node is awake just at the right time to hear that, and so on. And the signal passes along the line, and everyone can sleep except at the time step when they're supposed to hear the signal. And that means that, again, the signal took n steps to go across the path, but there was only 1 cent per node and only one listen per node as well. So that's a total energy of constant per node, compared with the other example where the listening energy was a lot more. So the moral of the story is you can save a lot of energy by not listening. And of course, the second moral is that knowing the topology makes a big difference. So if you knew the topology, you could just sleep until the appropriate time when the message is going to come to you, and wake up at just the right time and hear the message and transmit it further, and then go back to sleep and save a lot of energy. But what if we don't know the topology? Can we somehow infer the topology? So our goal is we want to assign each vertex a sleeping and waking schedule that will enable them to hear all the transmissions from their neighbors, but at the same time also save power by not listening all the time. So here's the model. We have n devices which are arranged in some unknown graph, and an edge in this graph is when two nodes are within transmission range of each other. Each time step a node sends or listens costs unit energy, and sending is not along the edges. A node can't decide that, oh, okay, I'm going to send a message to this neighbor of mine now. Rather, whenever a node decides to send, the message is received by each of its neighbors that happens to be listening. Except, what happens if a node decides to listen and more than one node within range decides to send? Okay, so this is like when lots of people are trying to talk to you at the same time and you can't hear anything because there's too much noise. So if two of your neighbors try to speak at the same time, you don't hear either message. There's two versions of these collisions. One is a detectable collision where you don't hear either message, but you do hear a disturbance. And another version is all you hear is silence. You don't even realize anybody is sending. Naturally, detectable should be easier, but actually both versions are pretty easy to handle with a known technique from IP packet routing called exponential backoff. So let's talk about what exponential backoff is. So let's simulate each time step with several like polylog n time steps. And if you've decided that this is a time step you're sending, then definitely send at the first time step of the simulation. And after that, each time you toss a coin to decide whether to quit or to attempt again in the next simulation time step. And if you're listening, then you listen for the whole round. That is, you listen for the whole polylog n time step. And what happens is that each time step, about half your neighbors decide to drop out. And so you have a decent chance that by the end of the round, you probably hear exactly one neighbor. Okay. Note that over the course of the algorithm, you can't really hope to hear from all your neighbors because you might have linearly many neighbors and that would cost a linear amount of energy. So our algorithms have to work even though there may be some neighbors we never hear from. Okay, so here's a little demonstration of backoff. Round one, everybody's shouting. Node at the center can't hear. Round two, half of them have dropped out. Round three, half of them have dropped out, and it happens that only one sender is left, and now the node at the center can hear. So from now on, we can assume that in each round, which is a polylog n time step simulation of one time step, you probably hear from one neighbor if you're listening and somebody is sending. A quick note about the graph. Radio communication networks are often modeled by some variant of unit disk graphs, but we won't make any such assumption. We'll just assume that we have any graph and the graph topology is not known to the nodes. And our algorithm will work even in this very general setting. We will assume that the nodes have some estimate of the number of nodes, n. Namely, what we need to know is we need to know a fairly good estimate on log n. If we know upper bounds on the number of nodes and the diameter and the maximum degree and all kinds of things like that, then we can take advantage of these to reduce the overall latency. But the only thing that we really absolutely need is an estimate on log n. Okay, so let's talk about the model again. There are n devices on an unknown graph, and an edge in the graph corresponds to being within transmission range. Each time step that a node sends or listens costs 1 unit of energy. And when a node listens, it receives a message from one neighbor if any of them are sending. And our goal is to design energy efficient network protocols. Ideally, what this means is we want protocols which run in poly n time and polylog n energy usage per node. Okay, so we've introduced a new model where we want to have algorithms that use poly n time and polylog n energy. And the natural question to ask is, okay, we've got a new model. Is it too easy? Like, can we do everything? Or is it too hard? Can we possibly not do anything in this model at all? And our answers are yes, we can do some things, and no, we can't do everything. So hopefully it's a good model. So let's address the no question first. If you look at the network diameter problem, it asks, how many hops apart are the farthest two nodes in the graph? And note that if the graph happens to be a clique, or if the graph happens to be a clique except for one edge, you can't actually tell these apart, because in order to tell whether a graph is a clique or not, you have to hear from all your neighbors. But you can't hear from n-1 neighbors using only polylog n energy. So it's hard to approximate diameter within a factor less than 2. And what do I mean by it's hard? I mean it takes linear energy. So we can't do everything. On the other hand, doing breadth first search gives a 2 approximation to diameter. So we will show a low energy breadth first search algorithm. So this will show that there are things we can do, and that's going to be the rest of the talk. Okay. So our goal is to do breadth first search. What's breadth first search? Well, there's a special vertex, the root. And for each vertex, we want to compute its graphical distance from the root. The naive BFS algorithm requires the vertices to be awake from the beginning, which is when the root starts transmitting, to d time steps where d is the diameter. And by this, I mean the worst vertex will need to be awake for that long. And that's too much time. So how can we enable, that's too much time because d could be linear, and we don't want anyone to be awake for a linear amount of time. So how can we enable vertices to sleep for a lot of that time? Well, if we knew the graphical distance to the root, we could sleep until just the right time. But wait a minute, we're trying to compute the graphical distance, so that's circular, so that's no good. Okay, what if we could get an additive estimate, like some magical estimate, g of v, for the graphical distance? And by the way, here I'm calling the graphical distance f of v. And suppose we had an easy way to compute some estimate g of v with the property that g of v is less than the true distance but g of v plus some constant is bigger than the true distance. Say the constant is 100. So g of v is less than the graphical distance, which is less than g of v plus 100. Then the node v could just wake up at time g of v and listen for at most 100 steps. And then by then it hears the message and hears exactly when f of v is. And then BFS would be achieved with constant energy usage per node, and every node could go back to sleep after it's figured out its distance. Alas, there's no such additive estimate. Okay, so we can't get an additive estimate. What if we could magically get a multiplicative estimate? That is, suppose we had an easy way to compute a function g of v such that the true graphical distance is between g of v and g of v plus 1 times polylog n. Well, then v could sleep until time g of v and listen from then on for polylog steps for until time g of v plus 1 times polylog n. And it would definitely be awake at the time the message reaches it, so that would be good. But unfortunately, and we call this polylog distortion, but unfortunately, this isn't even a constant factor improvement on the energy. So that's no good, except that this magic is real. In other words, we can get such a multiplicative estimate. So to summarize, we wish we could get an additive estimate because that would allow us to solve BFS in low energy, but we can't. We can get a multiplicative estimate, but that doesn't really give us a constant factor improvement. So where do we go from here? Well, it turns out that actually multiplicative estimates do help. So we're going to split the breadth first search problem into two parts. One is, how can we get these multiplicative distance estimates? And the other is, how can we use the multiplicative distance estimates to determine an effective sleep schedule? And of course, it will not be just wake up at g of v and go back to sleep at g of v times polylog n. Okay, so let's first talk about how we can get multiplicative distance estimates using low energy. The idea is that we'll partition the vertex set into clusters, and then we'll contract the clusters to form a new graph. And by that I mean that you think of each cluster as a vertex, and two clusters have an edge between them if there are edges between some vertex of this cluster and some vertex of the other cluster. And so now you have a smaller graph, and the idea is that we want to infer the distances in the original graph from the new graph. Okay, and we're going to create these clusters in such a way that each cluster has a known diameter. And so a path in the original graph has length at most the sum of the diameters of the clusters it intersects. And this is a simple consequence of the triangle inequality. And the question is, can it also be a good lower bound? So we want to know whether the distance between clusters gives us a good estimate for distances between vertices in the original graph. And the triangle inequality suggests that yes, it gives a good upper bound, but we want to know whether it's also a good lower bound. And theorem there is an integer r and a fast distributed randomized algorithm that partitions the graph into clusters such that with high probability, all the distances are scaled up by r up to polylog distortion. And what does that mean? It means that this algorithm constructs these clusters, and then for all v and w in the original graph, if CV and CW are the corresponding clusters, then the distance between the clusters in the cluster graph is at most r times the graphical distance between v and w, which in turn is at most polylog n times the distance between the clusters plus 1. So how do we do this? This is an algorithm of Miller, Peng, and Xu, and this is how it goes. Every vertex independently and identically generates a random number x from the exponential distribution with mean r. So you've got this random number, and you set an alarm for time r log n minus x. Now, what is this alarm for? Well, you wait, and when your alarm goes off, you form your own cluster of size 1. Except if you hear from a neighbor before your alarm goes off, then you join your neighbor's cluster and you ignore your own alarm. And once you've either formed or joined a cluster, you try to recruit all your other neighbors in the following time step. So how does this work? It means that clusters start forming at random times, and then they grow outward at a unit rate until there's no more vertices to recruit. And the whole process stops by time r log n, so that's an upper bound on the energy cost. Okay, so why does this work? Well, the maximum cluster radius is order r log n, and in dense regions of the graph, clusters are going to start forming early, and once they've started forming, they're going to start growing and they're going to get big. And in sparse regions of the graph, clusters are going to grow more slowly and they're going to stay small. But what do we mean by big and small here? We mean in terms of the number of vertices that have been recruited to the cluster. At the same time, all clusters are going to have approximately the same radius. So this algorithm was described and analyzed by Miller, Peng, and Xu, and later by Heupler and Wake. And they proved that particular edges in the graph are unlikely to cross a cluster boundary. We proved that additionally, with high probability, all the distances in the cluster graph are approximately the original graph distances scaled by r. And by approximately, I mean up to polylog n. Okay, so we can build this cluster graph, and the maximum cluster radius is O of r log n. And all the distances in the cluster graph are approximately r times the original graph distances. And so there's our multiplicative estimate, except how do we compute distances in the cluster graph? Okay, well, how do we compute distances in a graph? We do BFS. So let's do local BFS in the cluster graph. But how can we do it? I mean, how can we do anything at all in the cluster graph? Well, the beauty of it is that we can simulate any algorithm on the cluster graph in the underlying graph using only polylog energy overhead. Okay, so if we can do this, then we can do local BFS to get multiplicative distance estimates in the cluster graph. And maybe we can even do this for cheap if the parameter r is chosen carefully. And hopefully that means that we can get these multiplicative estimates. And incidentally, if the original graph was a square grid, then here's a picture of what the clusters could look like. Okay, so we can get multiplicative distance estimates using low energy. And that brings us to the second part, which is, given that we can get multiplicative estimates to determine, given that we can get multiplicative estimates, how can we use them to determine when we should sleep and when we should wake up? And remember that this is not as simple as just saying, let's sleep until the lower end of the lower estimate and then wake up and stay awake until the upper estimate, because that could be a linear amount of time. Okay, so what do we do? The idea is that we want to bootstrap the breadth first search process. So first we construct the cluster graph, and inductively we compute distances from the root to this on the cluster graph. And this is going to provide crude estimates of the distances in the original graph. And now, using these crude estimates, we can start running the naive BFS algorithm on the graph. And each vertex can sleep until its crude estimate time. Here's what the process might look like. So the red dot is where the BFS frontier has reached. The green region is all the nodes that are awake and listening. And the black region is the nodes that are sleeping or have gone back to sleep because the frontier reached them and passed by them. Okay, so every time the frontier advances one step, and some vertices are listening, others are sleeping. And at some point, a whole bunch of more vertices wake up because their lower bound on their estimate of the distance to the root has been reached. And then the frontier keeps proceeding, and so on. So as we already discussed though, if you just sleep until your original multiplicative lower bound on the distance, and then stay awake from then on until your upper bound, that could be a long time. It could be a linear amount of time. And that means that you're awake for a linear amount of time and spending that much energy, and that's no good. But notice that once you wake up, you don't have to just wake up and do nothing but listen. You can wake up and try to get a better sense of how far you really are from the frontier, right? So that's what I'm showing here with these arrows back and forth. Namely, when you wake up, you can actually try to get a better, you can actually try to recompute your distance in the cluster graph locally, and therefore get a better estimate on how far you really are from the frontier. And if you get a better estimate, then you can go back to sleep and sleep until that better estimate time rolls around. So we constructed the cluster graph and we computed distances, and then we want to do something like sleep until the lower bound, but we're not going to do exactly that. What we're going to do is we're going to use these lower bounds to determine a schedule for when to wake up, right? So at some scheduled times, some vertices are going to wake up and compute whether their cluster distance from the BFS is still less than some threshold, and you're going to compute how much slack they have. And anybody with more slack than that can just sleep through this process. But anybody who does wake up and who does participate for a little while can get a better estimate of their distance to the frontier, and they can use that better estimate to sleep longer. Right? So here's how it looks. And so these vertical tick marks here are the schedule for when you're going to wake up. And the red curve represents the actual distance in the cluster graph. And originally, your lower bound on your graphical distance is equal to a scaled version of this actual distance. And now what happens when the algorithm starts running? Every time step, your actual distance to the frontier goes down by 1, which means a lower bound on how long you need to stay awake is also going down as time passes by, right? So this blue curve here represents a lower bound on the actual distance in the cluster graph, and that decreases by something like polylog n over r each time step. Okay, so you sleep for a while. Initially your lower bound is the actual distance, but as time goes on, your lower bound is decreasing, but you sleep and you keep sleeping. And then at some point, I mean, if you kept sleeping all the way until this blue line hits 0, then that would be your estimate saying, okay, now you need to wake up and stay awake. But instead, before that, whenever this estimate gets lower than a certain amount of slack, you decide, okay, I'm going to wake up and I'm going to recompute. I'm going to recompute my distance to the frontier in the cluster graph, except I won't recompute it exactly because that might take too much energy. Instead, I'll recompute whether it's actually bigger than this threshold that is prescribed for that time step. Okay, so now my lower bound has gotten smaller than the threshold. So I wake up and I recompute, and I find that my actual distance is actually bigger than the threshold. So I set my new estimate to be this threshold, and I go back to sleep. And as time goes by, my lower bound keeps decreasing. And once again, I recompute when that lower bound gets smaller than the threshold for the time step. And notice that these thresholds, they are sort of dyadic, where periodically you're going to compute at a large threshold, but in between you're going to compute at half that threshold, and in between those you're going to compute at half that threshold, and so on. Okay, so here we are at this very large threshold, and we recompute the distance, and we find and because in this time step the actual distance is smaller than the threshold itself, we recompute and we find the actual distance in the cluster graph. And then we can go back to sleep and sleep until once again our lower bound is below the recomputation threshold. And then we wake up and recompute and go back to sleep, and so on. And this happens for some time. And then at some point, we recompute the distance, and the BFS frontier has reached the cluster that we're actually in. And at that point, we need to stay awake from then on until the frontier actually reaches us. So what's the upshot? There's a re-estimation schedule for the cluster graph that ensures that the clusters coordinate to re-estimate distances anytime some cluster might need to recompute because its estimate is about to hit 0. And a cluster's lower bound will not actually hit 0 until its actual distance is polylog n, by which I mean under the recomputation schedule, will prevent it from actually hitting 0 until the frontier has reached it. And this ensures that each cluster will sleep through all but polylog n distance recomputations. And so this whole process, any particular cluster, and therefore any particular node in the underlying graph, is only awake for polylog n of the time. Okay, but I told a little bit of a lie, because the algorithm needed to do local BFS on the cluster graph. In fact, it needed to do it multiple times, but we're trying to do an algorithm for BFS. So how do we do this? Well, we can do it recursively. So the cluster graph, again, runs the BFS algorithm and forms a cluster graph and so on, except all the cluster graphs at all levels can be computed at the beginning. And now the simulation of BFS on the cluster graph is again going to use its cluster graph and so on. So how do we analyze this? Well, we can set up a recurrence for the total energy cost. And it turns out that the solution is that the per energy node cost is at most this horrible thing, where D is some shared oracular upper bound on the diameter, for instance, n, right? Okay, so let's stare at this horrible thing. And okay, so what's the upshot? We've shown a breadth first search algorithm that runs in polynomial time and has a per node energy cost of 2 to the O of square root log D log n, which is not polylog n like we had hoped, but it is n to the little o of 1, so it is subpolynomial. And so you could consider that low energy. We also had a previous algorithm to solve the broadcast problem, where a message is going to be sent from one node to everyone, not necessarily along shortest paths. And that did actually use only polylog energy, but it took more time, although still polynomial. Okay. So I guess the moral is there's a trade-off between time versus energy use. And if you pay more, you could potentially sleep. I mean, if you pay more in terms of time, you could potentially sleep longer. Okay, so in conclusion, we've proposed a new model of energy-aware computation, and we've shown that some problems can be solved in the low energy setting, but it's not completely trivial to solve all problems in the low energy setting. Obvious future directions are to explore what other distributed computing problems can be solved. We have some ideas for matchings. Be nice to solve leader election or consensus, Byzantine agreement. Everything. It would also be nice to either show that breadth first search can actually be done in polylog energy, or show that it can't, and that our algorithm is the best. And there's a whole lot of open problems out there. So thank you for listening, and we hope that you will join us in thinking about this setting.